Find the volume of solid acquired by rotating about the line y equals 2, not the x-axis, not the y-axis, but rotating about the line y equals 2, so it will be a horizontal line. The region enclosed by y equal x and y equals x squared. Step 1, find the points of intersection, set y equal to y, and solve for x. When we do that, we get x equals x squared. And solving for x, we factor the left side, x times x minus 1 equals 0. That yields x equals 0 together with x equals 1. And then we get the ordered pair by plugging those x values into either of the two given functions to get the ordered pair 0, 0, and 1, 1 for the points of intersection. Those will establish our limits of integration in our integral. Step 2, we're going to do a sketch. We're going to use approximating rectangle that is perpendicular to the axis of rotation. They always have to be. All of the approximating rectangles and the disc themselves have to be perpendicular to the axis of rotation. So here we have our sketch, the y-axis, the x-axis, and we'll label some values on the y-axis so we can draw the axis of rotation. Y equals 2, the axis of rotation. We'll draw the little curly arrow to indicate that we're rotating the region about that axis. And here's our first point of intersection at 0, 0. So A equals 0 is our lower limit, and then B equals 1 is going to be our upper limit because those are our 2 points of intersection at 0, 0 and 1, 1. The upper function is y equal x. The lower function is y equals x squared. Here's our approximating rectangle with thickness delta x, which indicates we're going to have a differential dx in the integral. And it is perpendicular to the axis of rotation. So if we can imagine a three-dimensional view of this picture, here's the axis of rotation, y equals 2. Here's the x-axis, and we have the y-axis. And let's see, we are going to draw, this thing again sort of looks like a paper cup with some strange thickness on the inside. I've already tried to start drawing this disc that we're going to be cutting out of it. And you'll notice in the sketch on the left that both of our curves, both of our y equals x and y equals x squared, both live below the axis of rotation. That's important to note. So here's our disc that we're cutting out of it, and it does have a hole in the center, so it's one of the washers that we were discussing recently. And it's interesting to see how we're going to establish the outer radius area and the inner radius area, so we can take the difference between those two areas to get the net area of the face. So here is our washer, and we're going to put the center, going through the center is the axis of rotation, y equals 2. Let's see, we have, yes, a line. Well, remember this is an extreme close-up, so these lines are actually functions, lower function, upper function. And there's the y-axis. So we're going to first establish, let's see, the small radius, that's the inner radius, little r, that's represented by the function y equals 2 minus x. Oh, what do you mean 2 minus x? I thought you were going to say x. Well, I would have said x if the axis of rotation was the x-axis, but no, the axis of rotation is 2. So it's that value 2 minus the x. The outer radius, well, I would have said x squared is the outer radius had we been spinning this thing around the x-axis, but no, the axis of rotation is 2, so the outer radius is 2 minus x squared. It's that little distance right there. That little distance is x squared. So that, and that distance is x for our arbitrary location. All right, let's look at a bird's eye view of this thing. There's our inner radius, 2 minus x, and our outer radius, capital R, equals 2 minus x squared. So instead of having x and x squared, we have the 2 minus x and 2 minus x squared, since our axis of rotation is the number 2. Okay, now the area then would equal a of x as a function of x, the outer area minus the inner area, since there's a hole in the middle. So a as a function of x is equal to pi times capital R squared minus pi times little r squared, which means the area as a function of x is pi times parenthesis 2 minus x squared squared minus pi times 2 minus x squared. That's our area, the net area for the washer. So step 3, the volume thus is V equals the integral from the lower x value to the upper x value times pi times this strange radius. Okay, square the outside. I forgot to write a square. No, I don't write a square on the outside, my bad, because I just factored the pi out because we had pi capital R squared minus pi little r squared, so I factored the pi out. Then I found simplification, and now I'm finding the antiderivative so I can evaluate the integral. And that's equal to dot 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 8 pi over 15. You can calculate that to see that that's true. So the deal here was that we had to find the area of the outer minus the area of the inner. And then when I plugged that into the integral as the integrand, I just factored out the common factor, pi, and then eventually pulled that out in front of the integral.